So we continue with semiconductors today, part 4. Forward biasing and reverse biasing of semiconductor finds its application in rectifiers we have already seen. It converts AC to DC. The Zener diode acts as a stabilizer. The solar cell converts light energy to electrical energy. Today we are going to talk about LEDs and transistors. What is light emitting diode? What is the action? Let's see that. When PN junction diode is forward biased, energy is released simultaneously at the junction due to the recombination of electrons and holes. Such a junction diode is called a light emitting diode or a LED. Epoxy lens, the PN junction N region is heavily doped compared to the P region. It is encased in a transparent dome-shaped case. The metal electrodes act as an external contacts. That's the symbol of the LED. More than 2 LEDs are also available. 3, 4, 6 pins to obtain multicolor on the same LED. That's the structure. Now let's see the fabrication of the PN junction. It should be such that light should not be reabsorbed in the material. The electron-hole combination should take place to give maximum light. Compounds of gallium, phosphorus, arsenic are used. For example, aluminium gallium arsenide gives infrared light. Gallium arsenic phosphide gives red or yellow. Aluminium gallium phosphide gives red or green, or zinc selenium gives blue. On forward biasing, electrons from the conduction band combine with the holes in the valence band, releasing sufficient energy to produce photons emitting monochromatic light. The amount of light is directly proportional to the forward current. If a photon is emitted, then Ej is equal to h nu, that is equal to hc by lambda. Therefore, lambda is equal to hc upon Eg. Because of thin layer, sufficient number of electrons can leave the junction and emit colored light. Current rating is few tens of milliamps, so high resistance in series is connected. Forward bias voltage is larger in LED. So as you can see from the graph, it is more than one. This is the schematic structure of the LED, this epoxy lens, the wire bond, reflecting cavity, the anode and the cathode. Let us see the advantages. Energy efficient 135 lumens per watt. Long lifetime 50,000 hours or more. They are rugged. LED is called solid state light SSL since they are made of solid material and no breakable filament or tube or bulb. It starts in nanoseconds, so no form of time is required. Color rendering is so good that it does not fade. They are environment friendly. Brightness and color can be controlled. Disadvantages. Initial cost is high. It is temperature dependent. Some blue light may be hazardous. The applications: indicators and counters, burglar's alarm, optical communication, display screen of mobiles, television screens, headlamps of automobiles, illuminated decorations, street lights. Now let us see the structure of a transistor and discuss its working and application. The bipolar junction transistor, or the BJT, it has 2 junctions and 3 terminals. Current is carried by electrons and holes, hence known as BJT. There are 3 doped regions. So we have the PNP or the NPN type. So those are the structures. These are the symbolic diagram of a PNP and NPN. In 2 diode analogy, this is presented. Now, emitter is a thick, heavily doped layer. Supplies large majority of carriers for flow of current. The base, thin and lightly doped central layer. The collector, thick and moderately doped. Area is larger than emitter and base. It collects major portion of the majority carriers supplied by the emitter. Helps dissipation of energy, heat energy if generated. This is a structure. The emitter base junction is forward bias as we can see in the diagram. The barrier potential VEB is greater than 0.6 volts or 0.7 volt for silicon. The emitter current is divided into the base current and the collector current. So IE is equal to IB plus IC. So that's the emitter current. 0.5% of IE is a base current and 95% of IE is a collector current. Therefore, the base is very thin and lightly doped. Hence, IB is small. IC is almost equal to IE. Thus, for an NPN transistor, majority carriers are negatively charged electrons. Similarly, for a PNP transistor, majority carriers are positively charged holes. Transistor configurations. We have the common emitter C. This is for the PNP. The common base and the common collector for PNP. Similarly, you can have for NPN also the common emitter, the common base and the common collector. Common emitter configuration or the CE configuration. Now that's the circuit diagram. Input is at the base and the output is taken between the collector and emitter. It produces highest current and power gain. This is because input impedance is low as it is connected to forward bias part of the PN junction. The output impedance is high because it is taken at the reverse bias junction. We already know IE is equal to IB plus IC. Current gain is known as current amplification factor beta DC, as is defined as the ratio of the collector current to the base current. Alpha DC is equal to IC upon IE. From 2 and 3, you get IC is equal to beta DC into IB, that is equal to alpha DC into IE. From 1, 2 and 3, we can find alpha DC is equal to beta upon beta plus 1 or beta DC is equal to alpha upon 1 minus alpha. Common emitter characteristics. Circuit to study the CE characteristics as is shown. We have the IB, the VBE. While drawing input characteristic IB versus VBE, VCE is kept constant. When VBE is greater than the barrier potential, the characteristics are similar to the forward bias characteristic. The dynamic input resistance Ri is delta VBE upon delta IB. While drawing the output characteristic IC versus VCE, IB is kept constant. The dynamic output resistance RO is equal to delta VC upon delta IC. This is the output characteristic. It is the collector current IC versus the collector to emitter voltage VCE. The base current is kept constant. As the base current goes on increasing, the collector current also goes on increasing. Thank you. We'll continue next time.